Good evening to all of you. So, okay. So, in the last class, we were having understood the basics of NMR spectroscopy. We have moved to analyzing some of the spectrum in the finer details. And the first example was that of ethanol. So, where you have three different protons, different types of hydrogen atoms, but in different types of environment. So according to that, based on that, we found that you have, yeah, you are observing CH3 methyl protons at around 1.2. You are observing methylene, methylene, and hydroxyl. That's how you say. ठीक है ना? मिथाइलिन समझ में आ रहा है? CH2 प्रोटॉन्स को मिथाइलिन कहेंगे, उसको मिथाइल कहेंगे. And this is the hydroxyl proton. So clearly all the three types of protons are observed in at three different values of chemical shifts, and this is to do with uh, the electron withdrawing effect of the oxygen. So maximum effect is you can see on the proton that is directly bound to oxygen, and then you can think of the CH2 where oxygen is bound to the carbon and you have two hydrogen atoms, and the least effect is on this CH3, which is 2 carbon distance, so it is on the second carbon, alpha beta, so alpha beta carbon that you can see. So as the distance from the atom increases, the effect becomes less and less, and you can have this. And the ratio of the intensities, the collective, so you have you can see it is triplet split in there's it is not a single peak that you are observing for methyl proton. Instead, you are observing three peaks, so it's a set of which are spaced equally. Then you have quartet for CH2 hydrogen CH2 hydrogen protons from CH2. So we will take up this splitting pattern at a later stage. But what we also get to know about this, when you something that is interesting is the intensity when you carry out the integrated. So I introduced this term integrated intensity last time. So that is obtained by performing integration means in a graphical sense, that means taking area under the curve. So when you take the area under the curve, the ratio that this is the green plot that you are seeing is because of that. So it's a mathematical process which yeah, integration that you perform, and it is equivalent of taking the area under the absorption line. So this is what the green ones that we are talking about, the green color, the area of, for this is indicated by the green curve line over there. So if you take that thing, you find that the area under the curve has a ratio that is 3 to 1. So that is, intensity is directly proportional to the number of such atoms present, so number of such nuclei present. So you have three nuclei of in the same equivalent to each other, so they are having exactly same kind of situation. So that is the methyl protons. You have two protons which are having exactly the same condition under the same set of same environment. So you can see that intensity is proportional to this. Okay, so this is again obtained by software analysis that I told you, 3 is to 2 is to 1, or you can, if you are putting it the other way around, it will be 1 is to 2 is to 3. like that. So it helps when you have us perform this kind of analysis, looking at the splitting pattern we will discuss later. We are keeping it for later discussion, but looking at the intensity, looking at the, so there are three things that we can observe: chemical shift values, then intensity of the signals, then the splitting pattern. The splitting pattern we'll be discussing at very end, because it's a little bit complicated and we will work out the details, the reasons we will understand. So then what the more simpler things we are taking up first. So it is clearly, if you have three protons of one type, you can expect signal which will be higher as compared to one proton of same of another type. Okay, so that's how it happens. So uh, relative number of the magnetic nuclei of same having the same environment is important, and that affects the signal. So this is something that you are seeing clearly. And then the overall shielding that we are going, so the electrons will contribute to shielding effect, and the shielding will be due to three things: the local, the neighbor, the solvent. So the neighbor, local means immediately around that nucleus you have electrons of that atom which is being considered, so that is the local. And neighbor means the another atom is attached to that particular atom, and so that can also, it also has its protons, it also has electrons. So all these things may affect, they are, because affect the spectrum. So that is the thing we are considering over here. Neighboring group contribution. So so this is the second factor from any group of atom from rest of the molecules. अपना छोड़ के बाकी सबका जितना भी है उसको मिला सब नेबर है हमारे, नियरेस्ट नेबर, नेक्स्ट नियरेस्ट नेबर, एंड ऑल in such a manner entire molecule you can consider, except that particular atom. So all these are counted in neighbor, which is directly clearly covalently bonded, or in some cases may not be covalently bonded but suitably placed like that. Solvent contribution, so you dissolve it in certain solvent, so solvent molecules may also contribute. It also has electrons, electron cloud, it, and that can also contribute to the shielding. So the local, now we further bifurcate this local contribution into two types. D stands for diamagnetic, P stands for paramagnetic. So that diamagnetic contribution means there is reduction in the overall field that is experienced by the nucleus. Paramagnetic contribution means there is increase in the overall field, magnetic field, which is experienced by the nucleus. So this is the thing that, yeah. So how do we assign, so greater than 0, then you have it is a diamagnetic contribution. Less than 0, that means you are talking about negative values, that is paramagnetic contribution. So a positive value of the thing, contribution represents diamagnetic contribution dominates. A negative value of the overall shielding constant means it is the paramagnetic contribution that dominates. Okay, so so diamagnetic contribution is basically related to the ground state electron distribution, and when you apply magnetic field, they circulate. The ground state electronic distribution undergoes circulation, and that gives rise to this thing, and it can be easily calculated from the Lamb's formula as given over here. So diamagnetic contribution, so a closed shell atom only has diamagnetic contribution. There is no parametric contribution that you can think of for this, if you are considering the nucleus as here and circulating electrons around it. So so local shielding from the inner cores. So this is the only contribution in an atom, uh, which has because the core is spherical. In the inner core, which is completely filled, will be a complete shell will be a perfect spherical distribution. And so but when you are having a valence electron distribution can be distorted in a molecule, but the inner core will be spherical always. So this is the thing that we were talking about. You have a nucleus and the electrons are circulating. They generate another field. This is the secondary field that we are talking about, and it has effect to oppose. So you see at this point it is going like this. So it is opposing the field, and the applied field is in this direction. So this is what we mean by it tends to oppose the field of that is created, that is that is due to the applied magnetic field. So उसके opposite में रहेगा, and it will not be able to feel the full force, full effect of the applied field. So so in order to now, if you suppose if you have a fixed source of radio frequency, then you now need to increase the magnetic field to bring it to resonance. So that is the idea why we say that a high field region or low field region, chemical shift values having towards the 0 1 side, the lower side, in low value of chemical shift you have a high field region, and when you are moving to the other side you are having a large value of chemical shift. That means you are moving to a low field. So that's something, yeah. So so diamagnetic contribution, we already discussed electrons. So if you so what happens, we discussed this part, that if you attach say electronegative atom, then it withdraws these electrons. So electron density is taken away in the immediate vicinity in the of the nucleus, and because the electron density has been reduced, the diamagnetic contribution will be less, or you say that there is de-shielding of the thing. De-shield, not a complete de-shielding, but you can say there is slightly increase in the de-shielding of this thing when an electronegative atom is attached. And so this is something that we are talking about. Applied field is this from the magnet, external magnet. Electrons around it generate a small field which is opposite in direction. So effectively you are experiencing at the nucleus, this is the force experienced by nucleus. So this is clearly seen in case of so you need to so this is the reason why you have a shift in the values of this what we say del uh, chemical shift values are 0.23 in methane. Then if you add bromine, a little least electronegative among these on your screen, it is the least electronegative among the halogens, Vr, Cl and F, and some shift you are observing Cl, you are another shift, further shift in this manner. So this is clearly indicated through fluorine is electronegative, so you can clearly explain that. Nothing much to say on that count. And if you increase, if you one, so this is one point of view. having so one aspect of the electronegative atom, that you increase the electronegativity, the electronegativity of the substituent, you will have increase in the chemical shift value. Then you can also think of another way, that if you attach you increase you keep same value of electronegativity, but the number of atoms, so one Cl atom, two Cl atoms, three Cl atoms. So if you increase the number of the electronegative atom attached, that will also shift this thing. So this is having a greater effect. You can clearly see that the chemical shift value has moved to 7.27 by attachment by the same Cl, but number has increased. So the proton that is we are considering, the proton's resonance is now occurring at a less value of magnetic field. It is a de-shielding effect that we are seeing. And yeah, so depending on the distance from Cl atom, you can see Ha 3.42, then the next neighboring atom Hb. So you have 1, 2, A type, B type, C type, and last one. So all of them are having some influence, and they show clearly a shift from this. Next, you can see over here uh, oxygen, nitrogen, sulfur. So nature of the hybridization in the carbon, that can also affect, because yeah, so downfield shift. So downfield shift means a high value of chemical shift values. So it is inverse relation, ये आपको ध्यान में रखना पड़ेगा. When we say downfield, you are moving to lower magnetic field. You need to lower the magnetic field to bring it to resonance. And when we say high field, upfield, that means you need to apply a greater amount of external magnetic field. So this is clearly seen, oxygen, sulfur. So look at this. This is the oxygen replaced by sulfur, less electronegative, so less shielding, less de-shielding occurs, and the value is, so compare ether. This is ether, this is thioether. Ether, this is thioether. So you have replacement of oxygen with sulfur. The effect can be, so less electronegative atoms, what can, and they can, so here also in, similar thing as for halogens, we can see there when we replace chlorine with fluorine what happened, and here also sulfur with oxygen, you can see an effect. So and the nature of carbon at, so NCH3 hydrogen. So okay, so now CN. So these are the examples. Further some more examples of methyl protons with CO bond. Here oxygen is here, then you have ammonia N with CH3. So how, so this kind of thing, the electronegativity effect is clearly seen in this case also. When carbon is replaced with nitrogen, it shifts to higher chemical shift values. Okay, so so this was the local contribution that we are talking about. Diamagnetic contribution, we have already, it is due to ground state electron distribution which undergoes circulation when the field is applied. So now we will there's another contribution to the local field. As I told you, local field has two components, paramagnetic and diamagnetic. So diamagnetic is already discussed. Now this part, how can the paramagnetic contribution can arise? This can arise when you have suitable orbitals, you have the HOMO-LUMO gap is less, You apply magnetic field and the two wave functions are mixed. So that is equivalent of saying that the electrons are made to circulate, they are made to uh, somehow they make use of the unoccupied orbital, uh, which which are unoccupied in ground state. They can be utilized and the electrons circulate with that. So it is a kind of the you can talk in terms of wave function. There is mixing of the two wave function if the energy is gap is small between HOMO and LUMO, and this kind of thing can happen. So we will see where these cases arise. So local parametric contribution is 0 in free atoms and also 0 around the linear molecules such as ethine. So because the electrons are free to circulate, field and a field applied along the internuclear axis is not able to force into the other orbitals that we are trying to what we are saying. So it is importance of the low lying states. So the parametric contribution is related to low lying states or the gap, as I told you, HOMO-LUMO gap has to be small. In a molecule, if I am talking about, so you can have with so we'll see how it arises. So smaller is the atom, you will have greater is the effect of this, because small atoms usually they have the separation between, so energy levels, atomic energy states would be much less. So parametric contribution is dominant contribution for atoms other than uh, large paramagnetic contribution from small atoms in molecules with low excited states, low lying excited states. So actually we are talking about molecular energy levels, and the difference between occupied and unoccupied is small, then this contribution can arise. And in fact parametric contribution is, so atoms other than hydrogen you have this kind of dominance, particularly if I am talking about, so we can see we have a dominance of this effect in cobalt. We'll talk about this. So what happens here, that you have HOMO-LUMO gap, you can see here, applied the magnetic field, when it is applied the electrons can circulate, it is so small, this magnetic field causes an excitation through this, and now you can have circulation, what we were talking about, the circulation of electronic circulation because of the magnetic field using the unoccupied orbital is happening, that can happen. So this will have a paramagnetic contribution to the, if this happens, if the magnetic field is able to do this. And you can also see that very clearly if the Eg and T2G gap, the del value is, if it is small, you will have observed this thing more easily. This can happen easily for values if del is small, that is separation HOMO-LUMO gap del small, octahedral del not is small, you have that means HOMO-LUMO gap is less, and this kind of transition on application of magnetic field can happen. So easy external magnetic field causes field cause, it will lead to, when you apply, when this is small, it will cause this kind of so the wave function, so there is a mixing of the wave function ground state that with the excited state, or you can say that one of the electron, or in another way you can say that it is going to the so mixing of wave function can occur wave functions, that is, or mixing of the this kind of thing can happen, and you can have circulation of the electrons through the LUMO, which was unoccupied in the ground state, but on applying magnetic field it is happening. So low lying energy levels, this is what we mean, the gap has to be small, only then this will happen, and you can clearly see it happening over so a cyanide as ligand, CN ligand, you have a very high gap, so you can clearly see del not very high, nothing like this happens. High, no paramagnetic so the del value, shifting in the del value is very almost, it is zero. See, it is at this level. High, no such wave function, mixing of wave function occurs. Mixing of psi 1 psi 2 occurs. Homolumo, or you can say homolumo things, so that do not there is no such circulation of electron through this LUMO, and there is no such paramagnetic contribution is not there. But if you go to this point, so you see, as you gradually change the ligand, so carbon based ligand, now you see the nitrogen NH3 N ethylene diamine. So nitrogen based ligands, you can see they are having a substantially high value of chemical shift, and this is attributed to the de-shielding due to paramagnetic contribution. Paramagnetic contribution means this it increases the magnetic field more there is increase in the magnetic field, it is in this, or the magnetic field induced is in the same direction at the point of nucleus that is under consideration. So at the point of cobalt nucleus, we are having something like this. Cobalt is also magnetically active, so the nucleus of cobalt is magnetically active, and NMR can be conducted, and it has been found that there is change like this. So you can clearly see carbonate further lowering T2G is, del notch is small, very small. So in this case you are having this effect, the maximum shift is obtained, chemical shift values is maximum. And if you go to this, so 59 carbon is 59 cobalt is usually used for this kind of NMR in cobalt complexes. If you want to study the this kind of things, you can use NMR to understand the magnetic environment in a cobalt complex. So but here you have to so this is quite abundant. So here it can be seen because of this paramagnetic contribution, it usually a broad line in a broad range. So for cobalt 3 complexes will be obtained in a very broad chemical shift values up to this cobalt 3, cobalt 1 is obtained in this region, cobalt 0 minus 1 in the further on the other side of this value. So it is a 7/2 nucleus having I spin, I is equal to 7/2. So it is so whenever you have this kind of thing, it is this nucleus is having a not a dipole, it is a quadrupole, and the signal width increases because of the asymmetry of the environment. So the wide signals are obtained, you should also note that most common oxidation state of cobalt is 2, cobalt 2, plus 2 oxidation state, but plus 2 is paramagnetic. It cannot be used for, it is paramagnetic, that is you have unpaired electrons already, and it cannot be used for such purpose. This So in ground state you have unpaired electron, and it cannot be used for NMR. So the cobalt complex that is used for NMR is cobalt 3, cobalt 1, which is which has no unpaired electrons present. So observable species for 59 CO NMR, it is CO3, CO1, CO0, 0 oxidation state, and -1, 0 and -1. So these, but cobalt 2, which is the most common oxidation state, you cannot do NMR for that. It is paramagnetic, and you won't get any signal for that. So now we have the result that we were discussing, this halides. So there is also interesting thing about the halides, this alkyl halides that we were talking about. So if you look at this very carefully, you see, so you have on x-axis we have electronegativity of halogen, on y-axis we have this chemical shift values. So chemical shift value, by the way, it has been plotted like 1, 2, 3, 4. So it is increasing the downward side. So for the proton over here, look at the change in the chemical shift value with increase in electronegativity. It is consistently increasing. You can see increasing delta, that the chemical shift value is increasing for this particular H methylene proton. So methylene proton show a gradually increasing, almost a linear pattern. In a straight line plot you are getting for, if you compare the chemical shift values, if you plot the chemical shift value on y-axis and the electronegativity on the x-axis, so this is a typical pattern that you can observe. But the most interesting thing is that when you analyze this thing, the methyl protons show a decreasing trend in case of, remember you have decreasing trend of for the chemical shift, decreasing chemical shift values. Why is like this? So it is obvious when you have directly, when X, this halogen is directly linked to the carbon, then you have maximum effect over here, and electron withdrawing effect, and that can, so taking away the electron density from the vicinity of this carbon, and has some effect on the hydrogen that is bound to that, and so you can expect an increase in the chemical shift. Fine, but why does this decrease? The effect is, uh, you can see the increase in the decrease in the values of the chemical shift for methyl protons with electronegativity. So this is something intriguing, and it is related to what we know as magnetic anisotropy, something related to the anisotropic nature of the magnetic field, the non-uniform nature of the magnetic field. We will talk about this. So this methylene protons agree with the trend that is expected for considering the electronegativity things. However, the trend for methyl protons is opposite than expected, and something, so we are going to talk about the CH, so something related to CH and CX bond and their magnetic anisotropies, which is a dominant effect. And keeping this mind, so this is a neighboring group contribution that we are going to analyze. So let's see what happens. So the current, so look at the, So we have to look at the current induced in the nearby group of atoms and how they affect the proton of the neighboring HX, which is so electron distribution of X. So you have when you apply a magnetic field, it generates current. The circulation of electrons, that is belonging to X, and give rise to induced magnetic moment proportional to the applied field. So you have already learned in the previous second semester about magnetic susceptibilities. So so it is uh, so depending on how susceptible it is, each this halide ion will have different magnetic susceptibility, how easily the electron cloud can be distorted, how they can forced into circulation, how easily. So it is something that is important to realize is this: if think of a bar magnet. So if you see any magnet, the field that that it creates is non-homogeneous, it is non-uniform. So for example, look at this. This is north pole, this is south pole of a magnet, and when you draw the lines, it is like going like this in circles. So it is like a snake biting its own tail. So whenever you draw, so it is very different from what we draw for electric field. A magnetic field is always drawn uh, like a snake biting its own tail, right? So यहाँ से ये निकला और इधर से अपने पूंछी को काट लिया. So so that's the thing that you see. Now if you think of, if you can imagine this thing, you can also think that this bar magnet will, if I place a mag, nucleus over here A, if I place at the site A, or if I place a nucleus at site B, then the effect is going to be different. The same magnet will have the direction of magnetic field will be here. The direction of magnetic field over here is like this, going like this. So see, it is the only locally we can. So we draw lines B naught, and we saw straight lines like this, but that straight line is only for a very small region. एक छोटे से एरिया के लिए हम वो स्ट्रेट लाइन दिखाते हैं, यूनिफॉर्म फील्ड की बात करते हैं. अगर एक बड़े एरिया को लेंगे तो कोई भी मैग्नेटिक फील्ड हमेशा हमेशा नॉन यूनिफॉर्म ही रहेगा. ठीक है. And somehow this is something like this happens, and you see an increase in the decrease in the chemical shift values, unexpected decrease in the chemical shift values for the methyl protons. So something like this will happen. How it will happen, you'll have slowly you will get that idea too. So whenever we usually draw schematic diagram बनाते हैं, हम B दिखा देते हैं कि एरो से कि ऊपर की ओर बढ़ रहा है. So direction of uniform, so we usually show it uniform direction, but it is true only for a small area, that's what we mean. So but if you are looking in overall a wider view, then the lines of force will be anisotropic. As I told you, it will be having a increasing effect. It can point in is this direction. Over here at the site A, it can point in this direction. The magnetic field is, so direction of magnetic field is pointing in left or right direction, depending on where you are placing it. Okay, in relation to this magnetic field, sorry, in relation to the bar magnet. So so if you are placing in okay, so already so if you are as I told you already, if you are placing something at a point A, it will feel force in the north direction, in this direction, whereas if you put it here, it will feel a force in this direction. A magnetic thing at point A magnetic nucleus at point B, both will behave different. It will behave differently because of the placement, not because of the nature of it. It's the site which is different. Okay, so facing in the north direction, facing field is acting on the south direction at the point P. So this is the case that can happen with any magnet. So even these electrons that we are in circulation, they will also behave something like this. Okay, they will also generate, there is a so the electrons are moving in a ring like thing, aromatic ring current, you can imagine. When the field is applied in an aromatic system or in anything, so it is easier to visualize this picture first. So you can visualize that there is simple, apply your concept of what you learned in class 11 12th, that in a ring, when you have, if a current is certain direction, how the magnetic field is produced. A similar conclusion you will come to a similar conclusion when you draw the lines of forces, that at some point it will add to the existing field, at the other point it will pointing in the opposite direction and reduce the overall field. So that can happen. So some points it adds to the field, in other points if it is it has to be reduced, so such as A and B. So if you have a magnetic field which is external, then this thing can happen. So uh, so in aromatic compound, particularly in benzene ring, you can have a ring current that can we imagine there is circulation of electrons. So this circulate, so you have a ring current, this green arrow, so green arrow you can see circulation of electron current along this. So look at this point, so you have a ring current, and because of the ring, so this is your ring current, right, moving in this direction. And this ring, because of the, moving electrons, you have magnetic field produced. So this is the magnetic field which is going like this in circles. Now you imagine this, if you so this is what is happening, you have applied a magnetic field B. External magnetic field is this is the external magnetic field. This is what external field, magnetic field, and the ring is in circulation. The electrons are moving in a ring like pattern, and due to this motion of circular motion of electrons on a ring, you can imagine another magnetic field that will be produced. So this magnetic field, the produced because of the ring current, so this is the ring current gives rise to another magnetic field which is pointing in this way. So now think of it, look at the hydrogen which is here in the plane of the ring. This is hydrogen atom in the plane of the ring, so the B is pointing in this direction, it is pointing in this direction. So the magnetic due to the ring current, the magnetic field produced is pointing in the same direction as the external energy. It is the induced magnetic field is in the same direction as the, it has the same direction as the external field B. So induced magnetic field has the same direction as this thing, so it adds up, it is contributing to a paramagnetic effect. It is having it will cause an increase in the overall field that this hydrogen atom feels. So you can imagine the same thing will happen to all the hydrogen atoms which is in the plane of the ring. अगर एरोमेटिक रिंग के प्लेन में हाइड्रोजन एटम है, it will experience a net increase overall greater magnetic field, because both the induced magnetic field and the external field are pointing in the same direction, so they add up, and so there's both add up and you have increased net magnetic field. So this will be experiencing different. But think of a substituent which has a hydrogen over here, hydrogen atom placed over here. In this, at this point, the the magnetic field induced, B induced, is pointing in the downward direction. The magnetic field is upward direction, external magnetic field, and this field is acting in the downward direction. So both, this will subtraction, you need to subtract it for the net, to find the net field, and also you can have a reduced magnetic field at this point. This hydrogen atom placed over here above the ring, which is a part of a side chain, a substituent placed on the ring, that will experience a net reduction in the, so this direction of induced field is opposite to the thing, and so there will be reduction in the overall, reduced magnetic field overall, because it is pointing in the opposite direction. The induced field is opposite to the external field. So so it's the hydrogen above the plane, which is maybe a part of a ring, can have different values. It will be less experiencing less thing. So the same thing will be reflected in the NMR values, the chemical shift values that you can have. So you can expect, so what do you expect? You expect that protons attached to the ring directly, and the one that is above will have, so shielded, that is you have this one is deshielded, and this one gets shielded, or you have increased that way. So this is the thing that can happen. So accordingly you can have a change in the values of the thing. So by the same amount, so sigma b naught, we can relate this induced field is this is the induced field. So induced field is sigma into b naught, and you will have, so this one is experiencing this one, and here you have increase, and this is the external field, this is the induced field. So anything above the ring will experience a net reduction. So you will have to apply if you want to bring it into resonance, you will have to apply a greater amount of external field. And for these things, for the hydrogens atom, the protons that is in the plane of the ring, they will experience, they will come into resonance at a lower applied field, lower value of external field. Similar thing can happen to carbonyl compounds, double bonds. So we can have two things here, CC double bonds and CC triple bond. So in these cases also they will be, you can, when the magnetic field is applied, so this is the external field, so these are the external fields shown here over here, and so there is circulation of electrons, and you can expect, accordingly you can expect this field to be behaving like this. So this current will be having, when the field is applied in this direction, the ring current, due to the ring that you see over here, they are pointing along this direction, so it is curling up. So here it is like this, going up, adding up, and there should be, okay, so pi electrons, so it is the pi electrons circulating in a plane along the bond axis, along the bond axis, and a secondary field is created which acts on the proton, which is again in the same direction. You can see this is adding up, it is curling like this. So this is the direction of magnetic field, it is adding up. The direction of this is B naught, the applied field, and for these protons to be considered, you can clearly see that it adds up. So you can expect overall de-shielding will be there, and they will appear at larger chemical shift. Similarly, with an aldehyde, you have two things in combination that is operating. There is this ring current kind of this due to the pi electrons, and you also have electronegative oxygen that comes into picture, and so even greater amount of greater shift in the very large value of the chemical shift is obtained. So there is chemical shift is larger in case of carbonyl as compared to this kind of CC double bond ethylene. So we are comparing ethylene double bond with a carbonyl double bond. In both cases, there will be effect on the substituent, the hydrogen, the protons that is attached to carbon, but in both cases you are seeing that there will be net increase in the field, considering only if you purely consider the ring current due to the pi electrons circulation, both add up. So external field and this. Further, in case of CO, C double bond O, if you compare with C double bond O, oxygen is more electronegative, so that also is a factor which can affect the hydrogen that is present. Yeah, so this will further withdraw the electron from the vicinity of this carbon and the hydrogen because of the inductive effect, and so you will have finally, so that will also add up to the thing, de-shielding. So that's why carbonyl protons appear at a larger value of chemical shift as compared to CC a proton attached to CC double bond. A similar thing you can talk about for acetylene. In case of acetylene, you have the ring current, so it is a linear molecule in this case. So CC, if the field applies is along, if you apply a field along the internuclear axis like this, the electronic current is very smooth like this. It is so in the you are noting one point that in this case CC double bond you have a node, but here in this case in acetylenic triple bond, so CC triple bond that we are talking about, there is symmetric distribution of pi electrons. So this is pi electrons having a symmetric distribution around the bond axis, and they circulate. So they are circulated in a throughout the bond axis. You can imagine their circulation around this. So this kind of thing was not happening in this previous case, ethylene case. Okay, such because of there was nodal plane in the bond along the double bond in the double bond case. So now you will see that in this case what will happen. This is the applied field direction, this, and what you see here, the circulation of electrons in this manner is opposing it. So this is the induced, so sigma B naught, so this is the induced one. Induced field is opposing the applied field. So this in case of CC protons are attached to this thing. Here also you can see this is opposing the field. V naught is in this direction, so B naught, and this is the sigma V naught. So both are in opposition to each other. So both the methylene sorry acetylene protons will appear. They are shielded. There is reduction in the magnetic field, and so they will appear at a smaller chemical shift values. Okay, so this is so that is so there is a okay, so this is something that we probably saw in previous slide where we had, so look at this. So you can correlate this with the previous slide, number 33. You can see this here, CC double bond CH ट्रिपल बॉन्ड का नहीं दिया है. अच्छा, appearing over here some values somewhere. नहीं, no, I have not shown in my slide here. Okay, anyway. So this was the thing, and in a similar way so finally so figure V, that is of the acetylene protons, we can see that the protons are clearly shielded. That is what I was talking about. You have applied field, sorry, the induced field which is opposing the applied field. So B naught is in this direction and sigma B naught is in the opposite direction. So they get this effect is very large. This ring, whenever you have a ring current, that will be very large. And although you have sp electron, so you can so because here the sp carbon, it is sp carbon, this is sp2 carbon in ethylene, but here sp hybridized carbon. So you expect the electrons to be withdrawn towards carbon more. It will be attracted towards the carbon nucleus more, and not lying towards hydrogen. But that de-shielding is less as compared to this huge effect of the ring current. And so you have yeah uh, so this is what you observe for. So the methyl and the acetylene and ethylene, the nature of protons, the chemical shift values will be totally different. In one case you are getting, so this is a very contrasting nature that we have just discussed. In one case you are having a highly shielded proton, in another case you have highly de-shielded protons. Okay, so the neighboring group contribution can be further analyzed. So this thing I can discuss tomorrow. It will slightly, yeah, you will take time. This is something more, you will need time and I will need your attention more on this. So let's do it tomorrow. I will not keep it long. So I'm winding up here. We'll do it tomorrow. Tomorrow नहीं, कल आप लोग तैयारी कीजिए नेट की. We'll meet after your net exams. So I don't know. Okay, so let me just